right. So, as we mentioned before, okay, having hydrogen produced by our reaction is probably not our best bet. We probably really would like to have other reactions that don't produce such dangerous byproducts, okay? We want the heat. We don't want a chance of fire or explosions. That's pretty safe bet. Huh? Right, and you know, ice cream, exploded ice cream is not as good as non-exploded ice cream.
It's really light, though. It's
So, the issue here is that we don't want to have to go in the lab and conduct so many experiments. We don't want to have to go through and look up so many different values of all of these experiments so that we can put all the equations together and make a map, okay? There's got to be a better way to go about doing this, okay? What we really need is a list of standard values. We need a way to do this so that we don't have to have a whole bunch of equations. We want to be able to work on this and we can simplify this if we have a set of standards. If we have a way that we all write certain equations the same way, then we can go ahead and use just these standard values. And the way that we do that is by looking at what we call the enthalpy of formation. We can take a bunch of compounds, molecules, and we can look at how they are formed as a way to sort of generate automatic Hess's law equations. We know that, you know, Hess's law is where we take the equations and flip them and multiply them. If we simplify the equations and write them in a certain way all the time, we can get rid of that whole flip it, worry about all that kind of stuff, equation stuff. The basic idea is this. Let's imagine we have a chemical reaction. This is another one that exothermic reaction. Sodium metal reacts with carbon dioxide to produce sodium oxide and carbon monoxide. What we are going to imagine is this chemical process, this chemical reaction where the bonds are rearranging, we're moving electrons around, as a process of breaking the bonds here to form individual atoms, and then rearranging those atoms to form our new reactants. So our sodium, well, that's already sodium. But the carbon dioxide is really carbon and oxygen. We're breaking it down into its elements. Okay? And then what we're imagining is these elements recombining to form our new products. So, what we want to do here with the oxygen going to the sodium and the oxygen, the carbon going to the carbon monoxide, the sodium recombining with that oxygen, is we want to be able to write equations that represent the formation of each of our molecules, both the reactant molecules and the product molecules. If I form sodium oxide, I form it from 2 sodiums and half of an oxygen molecule to make 1 sodium oxide. And this is the convention. We always write these equations so that we're forming 1 of the thing that we're talking about. The enthalpy of formation, the equation for the formation of sodium oxide, has 1 sodium oxide molecule. And yes, we have to use fractions, okay? And we start with elements, individual elements, in their natural elemental state, we say, okay? So, oxygen always comes as a diatomic. Remember the Hahn-Fickelbers? The diatomic molecules, they're going to come as 2. Sodium is an element, comes as individual sodium atoms. How about the formation of carbon monoxide? What's carbon monoxide formed from? Carbon and oxygen, right? So we have an equation for the formation of carbon monoxide. That's essentially this half of the reaction, the formation of these guys from their elements. Yeah. Now the other half of this is we still have these guys here, the sodium and the carbon dioxide. So the formation of carbon dioxide, again, is going to become from carbon and oxygen. That's the formation equation. And what about the sodium? Now, sodium is already an element. I don't have to worry about that. I don't have to write a formation equation for sodium. Sodium is sodium. Nothing changed about it. So there's no reaction. Essentially what I'm going to do is I am going to do Hess's law with these equations. Okay? I'm going to do Hess's law with these equations, and then I'm going to show you a real, and we can see that, right? What I need to do, I need to take this equation, and I need to flip it around. Okay? And I'd have to, and that would be it. Right? I have 2 sodiums. I flip this equation around, and I've got it. It's okay. Now, because we are going to write these formation equations the same way every time, that is formed from the elements in their natural elemental states and always producing one of the target molecule, one of the thing that I'm talking about. So this is the formation equation for carbon dioxide. This is the formation equation for carbon monoxide. This is the formation for sodium oxide. Because I'm writing those in the same way every time, I can create a table of standard values. I can create a table of the enthalpy of formation values for all kinds of elements. And you were given a table of that when you walked in today. Okay? That thermodynamic data has delta HF values. So now, instead of going through and trying to figure out how do I flip around all the equations, because all the equations start from elements, I don't have to worry about them. They'll automatically cancel out. All I need to do is look up these formation values and take the sum of the products, the sum of the values of the delta H's for the products, minus the sum of the values for the reactants. Products minus reactants. Delta H for the whole thing is going to be equal to the delta HF values of the products minus the reactants. So in this case, what are my products? I need to look up delta HF for sodium oxide. I got one of them. If I had a 2 here, I'd multiply this by 2. It's per mole value. I got to take into account the coefficients. I got to include that. Carbon monoxide, I got one of them. My reactants are what? Sodium metal, notice the 2, so I put a 2 in front of the sodium metal. And carbon dioxide. Now I take out the sheet, or I look in a big book, and I look up these delta HF values that people have determined experimentally. People have gone in the lab and conducted experiments for us already. Okay? So we look up those values, and I plug them in. Negative 416 for sodium oxide, negative 110 for carbon monoxide, negative 393 for carbon dioxide. What do we notice about the sodium? 0. It's already an element. Formation of an element from itself is no change, 0 energy involved in the reaction.
I thought you said you wanted to flip the C plus O2, just CO2.
Yeah. Remember we had that equation? I said we got to flip it around? Guess what? Because of the way we do this with the negative sign right here, that takes care of the flip for all of the reactants automatically. We never have to flip the products. Because of the way we're writing these equations, always from elements, we just have to flip all the reactants, and that's it. And this negative right here, we don't need to worry about anything. If you're working with enthalpy of formation values, you look them up, sum of the products minus sum of the reactants, you're done. Okay? In the problem, they'll give them to you. Or they'll give you information to find them. Remember, there's a sort of reverse thing that they could do here, which is not infrequent, where, this is equal to delta H, right? So if you knew the delta H, and you knew all of the delta HFs but 1, you could solve for delta HF. Right? Essentially, you have a certain number of variables, and you're going to be given all but one of them. So, key, delta H equals sum of the products minus the sum of the reactants. This is super easy. I mean, it's easier than doing the Hess's law. Hess's law, you got to figure it out. You got to flip them all around. If we write the equations all the same way every time, you just look them up on the chart, add, and you're done.
On the paper, it says delta H equals to negative 809. Is that a typo?
Which one? For, yeah, there's a typo someplace. Probably on the handout. I have to remember to fix that.
So if they're telling you to use the Hess's law, but could you technically solve it by doing this instead? Like you don't have to.
Yep. You only have to use Hess's law if they say do Hess's law. Or on a test, they don't give you the delta HF values. You can't do this process.
What if you like remembered all of that?
I don't know. That would be interesting. I don't know what they would do. That's a good question. I think that's probably unlikely. All right, so do it. You have the chart. I'll go turn the lights on in a sec. This is the equation. Silicon tetrachloride reacts with water to produce silicon dioxide and hydrochloric acid. What's the delta H for this reaction? That's your task right now. All right. So, products minus reactants. Delta HF for silicon dioxide plus 4 hydrogen ions plus 4 chloride ions. Those are my products. Remember, the key here is that HCl, strong acid, does not form in water. You can't find HCl stuck together. There's an energy change associated with it breaking apart. They can have different energies. Products minus reactants. I got 1 silicon value for silicon tetrachloride, 2 values for water as a liquid. Liquid and gas takes energy to change between them, so you got to grab the right one. Okay? So we look on the chart. I plug in, look up all these values on the chart. Silicon dioxide, negative 111. Hydrogen ions is at 0. It's our standard state. It's one of those things that we define as 0. And then we have the chloride ions, 4 times negative 167. Silicon tetrachloride, negative 687. 2 times water as a liquid, negative 286. Did you get negative 320? Should double check your math. If you have these values, this is what the answer you should get. So check things where people make mistakes. Did you grab the right chlorine? It's hard to read. Chlorine is negative 167. That's the chloride ion, not Cl2 liquid or Cl2 gas or whatever. Did you grab water as a liquid or water as a gas? Those are the easy mistakes to make. Those are the most common mistakes. It's got to be the exact right thing. Phase matters because phase changes take energy. So water as a liquid versus water as a gas have different energies of formations because it takes energy to change the liquid into the gas. All right? So, products minus reactants. That's it. Look them up on the chart. Okay? But wait a minute. I can't leave well enough alone. There's another way to do these calculations, a more fundamental way in some aspects. Okay? We can deal with this in terms of bonds. Chemical changes, the chemical reactions we're dealing with have energy changes because of the changes in the bonds that are being formed and broken. Okay? So we can look up the energy involved in a chemical bond and use that as the basis for calculating delta H values. Okay? So, example. Here is a chemical reaction. Okay? I have methanol reacting with carbon monoxide to form methanoic acid. Okay? We're forming this carboxylic acid from the methanol and a carbon monoxide. The way that we look at these problems, if we have bond energy information, and it's really clear to tell when you have to do this, the problem will give you a table of bond energies. Okay, literally it'll give you a bunch of bond energies and ask you to do work with them. It works basically the same as the standard enthalpy of formation, except it's reversed. So what we need to do is we need to find out what are all of the chemical bonds that are broken. I'm going to take all these reactant bonds and I'm going to break them apart. I have carbon and hydrogen bonds in here. How many carbon-hydrogen bonds are there? So I have to look up the energy for one of them and multiply it by 3. So these are all going to be broken. I'm going to have to go through and break these. I'm looking, the way that we calculate it is break everything down into atoms and form it all back new. Okay? Lewis structures are definitely of help in doing this, which is why I put some Lewis structure stuff in here to help us see where, because a carbon-hydrogen single bond has got a certain amount of energy, and then a carbon-oxygen bond is going to be different, and oxygen-hydrogen is going to be different, and a double bond is different than a single bond, and in reality, a double bond next to a single bond is different. Both of them are different than if they're isolated from each other. Okay? The atoms that are around it, other atoms that are connected to this carbon does have a change on this value. Now, we typically don't worry about that. We typically just use average bond energies, but that makes this a little suspect. You have to, if you want to be very precise, you have to consider what's connected to this carbon. The fact that there's another oxygen here is going to change the interaction, going to change the strength of those bonds. It depends on how they're connected. In this case, this bond is weakened and this bond is strengthened, and this hydrogen-oxygen bond is weakened. So it's complex and not anything you need to worry about, except in a very generic sense of saying, hey, bond energies are average values. They can be, maybe they're more likely to be a little bit off, because they're, in average, they're not taking into account the specific shape or relationship between the different bonds and how they affect each other. So in addition to the carbon-hydrogen bond, I have a carbon-oxygen bond. And I have an oxygen-hydrogen bond. And I have a carbon-oxygen triple bond. These are the bonds I have to break to get back to individual atoms. Now, what bonds am I going to form over here? I've got the carbon-hydrogen bonds, and I've got 3 of them. I've got a same carbon-oxygen bond. I still have an oxygen-hydrogen bond. And what else? What's the other bond I got? I have a carbon-oxygen double bond now instead of a triple bond. That's this CO here basically ended up right there. The energy in the bonds is going to be given on a table, which is actually in your homework packet. I put together your homework packet so it has a table of bond energies in it, usually kilojoules per mole.
So it's the energy of all those bonds minus the energy.
So this is where it gets a little tricky. It always takes energy to break bonds. It takes energy to break bonds. Well, I'm going to say almost always, although I cannot think of a single example where that wouldn't be true. Okay? And energy is released when bonds are formed. Okay? Bond forming releases energy. Always. Almost always. I can't think of an example where it doesn't work that way. But the universe is a strange place. So, forming bonds releases energy. Okay? If you haven't taken biology yet, when you go to take biology, make sure that they tell you that forming bonds releases energy, because forming bonds releases energy and breaking bonds takes energy. Always. Okay? That's important, because sometimes the biologists don't think of it in that specific detail. They like to think about it just overall. And they say, oh yeah, we broke the ATP bond and energy was released. No. You formed some new stuff that released energy. Breaking the ATP bond costs energy. It takes energy to break bonds, always. Because these are attracted to each other, pulling them away takes energy. These are attracted to each other, coming together releases energy. So to get the signs right for energy absorbed or released, what we have to do is we have to, oh, I left out a bond, didn't I? I left out the carbon-carbon bond. I'm sorry. This carbon to this carbon. My apologies. Yep, the same bond. Yep. So this carbon-hydrogen bond here has the same energy as this one to a first approximation average values. In reality, because we've added some other stuff over here, it might influence it. So what we're going to do is we are going to look up all these values 3 times. It turns out the carbon-hydrogen is 413. We can add up all these values. And what we do is we take, instead of delta H, products minus reactants, bond energies, reactants minus products. When we're dealing with delta HF values, enthalpy of formation, we said it was sum of the products minus the sum of the reactants. When we're dealing with bond energies, it's the sum of the reactants minus the sum of the products. Yeah, you could ignore everything that's the same on both sides. But I like to write everything out completely just so you can see what's going on. So this reaction has a delta H value of negative 20 kilojoules per mole. Delta HF is the most common type of problem to see on the AP test. Hess's law is next. This bond energy stuff is, for this aspect of it, the rarest. But does still occur. Okay, does still happen. Just not as much. Sometimes they do a little bit of each in a problem. They'll ask you to calculate delta H using standard enthalpies of formation, and then they might give you that delta H and ask you to calculate the bond energy that's missing from this equation or something like that. They like to string problems together like that. You'll see examples next week. I've got a couple more worksheets for you to do next week, in addition to some more lab activities. Anything that I'm asking you to do a big write-up for? No, not necessarily. All the little just do the calculations, write me a conclusion. Yeah. So the stuff we did this week, that's the 2 we did this week. Yeah, I expect you to have them done on Friday.
Do you want a full write-up thing?
No. Nope. Just give me, so the one we did yesterday, just do the calculations. On that sheet of paper, treat it like a worksheet, do the calculations. That's it. The one we did before that, the specific heat capacity, what I want you to do is I want you to give me a 1-page write-up. Not a big, multi-page thing. Rewrite your calculations, clean it up, a little introduction, some calculations, a conclusion. You should look up what's the specific heat capacity of your metal. Right? So go to the NIST, National Institutes of Standards and Technology, NIST.gov, and look up metals and specific heat capacities, or go to Wikipedia and look those up. Okay? The 3 metals you had, the 3 options were copper, iron, and aluminum. Copper, iron, and aluminum. Make your best guess about what you think it was. Look up the specific heat capacities of all of them. Compare. Tell me your percent error. Tell me why you think what metal it was. Okay? Yeah, I think we should make ice cream too. It's just a little chilly to do that. Although not in this room. All right, so we've got it. We've got we can make ice cream in the woods, no big deal. We can use our nice, easy to transport chemicals. We can make froyo. It's a perfect accent to our ice cream cake. Yes, don't eat these. Any of these chemicals.